So now I want to review the rotating frame description of the magnetization, because this is really important that we have a good grasp on this description. So the equation of motion for the magnetization has to be valid in any reference frame in the presence of the magnetic field is given by the Larmor equation, which states that the magnetization precesses around delta B effective with the frequency gamma delta B effective. If the B effective is along Z, then this means that the magnetization will precess in the XY plane with a frequency that's given by gamma delta B effective over 2 pi. Now let's look at the rotating reference frame. So we have a reference frame that rotates around Z, about Z, with a frequency omega RF. Let's take the first case. The rotating reference frame does not rotate. That's the lab frame. That's what our reference frame. So omega RF is 0. In this case, the magnetization precesses in the XY plane with the frequency gamma B0 over 2 pi. So if we take the reference frame here, we have the B0 here. We have our magnetization here. We're just putting the magnetization at a certain angle. So we're just looking at the component that's transverse. Let's affect this component here. The component that's perpendicular to B0 does not precess. So this magnetization here, the transverse magnetization, will precess with a angular velocity omega L. So its angle will increase with omega L t. It goes around B0 in circles the transverse component. So if we take the transverse component, then the transverse component will simply do this motion. That's the Larmor equation in the non-rotating reference frame. Now we'll take the second case, and that is the rotating reference frame. And now we'll place ourselves into the rotating reference frame that rotates exactly with the Larmor frequency. In this rotating frame, as we are rotating exactly with the magnetization, this magnetization is by definition stationary. It does not move, or in other words, it precesses in XY with 0 frequency. Now, the equation of motion that we have up here still has to be valid in this reference frame. So the precession frequency is equals to gamma delta B effective over 2 pi, or in this case, the delta B effective will be 0. And our magnetization will do this motion, namely none, because we are in the reference frame where it doesn't move. Now, the Larmor frequency in big omega in the rotating reference frame is given by gamma delta B effective. And this delta B effective is given by B0 minus omega RF over gamma. So what this means is we are to get from here, the lab frame, to the rotating reference frame that rotates with the Larmor frequency. What we have had to do to still have the equation work, we had to subtract the fictitious magnetic field, which was in this case equals to omega L over gamma, and omega L is gamma B0, so the delta B effective was B0 minus B0 equals 0. But this holds true for any omega RF, for any angular velocity of a rotating reference frame, and we can calculate the delta B effective. Now here I want to make a short digression into quantum mechanics. Not what we strictly need quantum mechanics for understanding most of the MRI principles. We can actually work very much with the classical principle. But we want to remind ourselves that magnetic resonance is a quantum mechanical manifestation. It is a property, comes out of quantum mechanics. Quantum mechanics is the proper way of describing things. And what I want to do here is build a bridge between our description, classical description, and the quantum mechanical theory that's behind this. So let's look at the Schrödinger representation. We have the derivative of the ket is equals to the Hamiltonians times the ket. And if the Hamiltonian is constant in time, then we can write the solution very simply. The expectation value of a operator Iz is given by this term here, in the Schrödinger representation. So this is all standard theory from quantum mechanics. Now we have some equivalences here, and that is the magnetization along z is the expectation value of the operator Iz, the magnetization along x that of Ix, and the magnetization along y the expectation value of Iy. So in other words, our macroscopic quantities that we observe, the magnetization, are the expectation values of the quantum mechanical operators associated. So this is very nice. So for a spin 1/2, let's say the hydrogen nucleus, the proton, we have two energy levels. So we have, this is the operator for Iz, Ix, and Iy. These are the Pauli spin matrices that describe the system. Now, how do we determine the time dependence of Ix, that is, of the mx magnetization? And the way this is done here is we split the Hamiltonian into time invariant and time dependent terms. So we can write our Schrödinger equation here. We'll split the Hamiltonian, this term here, into time invariant term here and a time dependent term. And then we impose that the time invariant term is much bigger. Its eigenvalues are much bigger than those of the time dependent term. And we'll use here now the interaction representation, which comes from higher order perturbation theory. And if we do that, the transformation that is being done, that comes out of this theory, is that we have now the ket in the interaction representation, and we will now, under this condition, the representation equation of motion for the wave function becomes this term here. And we have now the v of t is transformed to the v in the interaction representation. This is the transformation given here. Now for a nuclear spin, this is all general theory. Now for a nuclear spin, the static Hamiltonian is the one associated to the magnetic field. That's the one that generates the two energy levels. Hence we have Iz here as the operator. And we can take the time variant Hamiltonian given by this term here. Now what is this, how does this transform if we do this transformation here, if we use an omega RF here in this term here that is equals to gamma B0. And actually if we do this transformation, we'll find that in the interaction representation, this time variant term here, which we have in this term here, becomes time independent. So the beauty here is that we have used classically the description in the rotating reference frame to make things stationary. If we do this in the interaction representation and we make our Hamiltonian in this representation stationary, we're essentially doing the same thing but in quantum mechanics, and we obtain now a stationary Hamiltonian. This is equivalent to putting ourselves into the rotating reference frame. So we have an additional quantum mechanical equivalences, that is the B0 is along Iz, is proportional to the operator Iz, and the B1 x or y is given by the operator Ix, Iy. That's what this term here is. This is the description of the RF field. So this is a short digression into quantum mechanics to remind ourselves that what is behind magnetic resonance is truly a quantum mechanical event.